Howdy. This video is on entropy. The second law of thermodynamics states that for every spontaneous change, there is an increase in the entropy of the universe. Now, spontaneous in this context just means that occurs without any outside intervention. So basically what the second law says is that for everything that occurs, the entropy of the universe increases. And so there's three laws of thermodynamics. The first basically says energy is conserved. It cannot be created or destroyed if you assume the universe is a closed system. The second says for every spontaneous change, there's an increase in the entropy of the universe. The third is that the entropy of a perfect crystalline substance is 0 at 0 Kelvin. And so entropy is a measure of the possible number of configurations of a system. And again, the universe is constantly going to a state of higher and higher entropy. And so it's best to think about entropy as using this equation. S entropy is equal to K, Boltzmann's constant, times the natural log of W, where W is the number of configurations. Now, some of you may have been taught that entropy is about disorder, a measure of disorder, but entropy is not about disorder. Disorder cannot be quantitative. Entropy can be quantitative. And so, if a process would decrease the entropy universe, we'd call that non-spontaneous. And again, in this context, spontaneous just means occurs without any outside intervention. If the entropy universe would increase for a process, we call that spontaneous, which again just means it occurs without any outside intervention. It doesn't say it occurs quickly or instantaneously, just occurs without any outside intervention. And so Boltzmann's equation, S equals K natural log W, is important enough that's actually on his tomb in Vienna. Now it's kind of interesting, on his tomb it's LOG, and when it was carved, LOG actually referred to as natural log. Now natural log is represented by Ln. So please make sure you understand the difference between base 10 log, LOG, and the natural log, Ln. And so entropy is related to the number of possible configurations a system can have. Again, S equals K natural log W, where W is the number of configurations. K is Boltzmann's constant, which is equal to 1.38 times 10 minus 23rd joules per Kelvin. It's interesting to note that the gas constant is actually equal to Boltzmann's constant times Avogadro's number. And so when we're talking about configurations, we could be talking about positions of atoms or molecules. We could be talking about relative orientations of molecules. We could be talking about ways of filling energy levels. And so a perfect crystal at 0 Kelvin has only one possible configuration. And so that would give you W of 1. And the natural log of 1 is equal to 0. And so that's how we get the third law, that a perfect crystal at 0 Kelvin has 0 entropy. And so we could ask, okay, which of these two flasks has higher entropy? In both cases, we have 1 mole of oxygen gas. In A, we have a 1 liter flask. In B, we have a 2 liter flask. Well, in the bigger flask, you'll have more places the gas can be, and so the B should have a higher entropy than A. Again, entropy is a measure of number of configurations. The more positions the molecules can take, the more possible configurations, the higher the entropy. We can think about 4 molecules of carbon monoxide in a box at 0 Kelvin. We think about 0 Kelvin because that means there's only one way of filling the energy levels. And if we imagine the 4 carbon monoxide molecules, they can face either to the left or to the right. And if we make that stipulation, there's only 16 possible configurations or 16 ways of filling the box with 4 carbon monoxide molecules. And so S equals K natural log W, Boltzmann's constant 1.38 times 10 minus 23rd, natural log is 16, and we get that the entropy of 4 carbon monoxide molecules in a box at 0 Kelvin should be 3.83 times 10 to the minus 23rd joules per Kelvin. If we think about this tetrahedral molecule, so we have chlorine in the center, fluorine at one end, and then 3 oxygen atoms. And so we can actually arrange it in 4 different ways. So the fluorine could be in this corner, that corner, that corner, or that corner. Now if we have a mole of these molecules, the number of configurations would be 4 to the power of n. And so natural log of 4 to the power of n, that n can actually come out. And so now we have entropy is equal to K times Avogadro's number times the natural log of 4. If we calculate that out, we get the entropy of this system would be 11.5 joules per Kelvin. And so it's really kind of cool. In some cases, we can actually calculate entropy using this equation. Typically, we have to stipulate 0 Kelvin because it's kind of complicated to talk about the number of configurations of filling the energy levels. And so if we look at two systems with a different number of energy levels, and so we're assuming the two systems are at the same temperature, the system with the more energy levels, there's more ways of filling it, more states that are accessible, more possible configurations, hence the higher the entropy. And so we'd say the one on the right has a higher entropy than the one on the left. And so again, in terms of configurations, you can be talking about positions, orientations, or ways of filling the energy levels. At 0 Kelvin, there's only one way of distributing the molecules among the energy levels, which is why the third law states that for a perfect crystal at 0 Kelvin has 0 entropy. And so S equals K natural log W. Again, W's number of configurations could be positions of atoms or molecules, relative orientations of molecules, or ways of filling energy levels. Now we can convert this into thinking about a little bit more easy way concepts. And so in terms of compositions, the more atoms per molecule, the more energy states you have, and hence the higher the entropy. In terms of intermolecular forces, the stronger the intermolecular forces, the less configurations and the lower the entropy. In terms of physical states, gases have more possible configurations than liquids, which have more possible configurations than solids. So gases tend to have higher entropy than liquids, which tend to have higher entropy than solids. For a specific compound, the gas will always have a higher entropy than the liquid, which will always have a higher entropy than the corresponding solid. And then in terms of temperature, higher temperature always leads to higher entropy because higher temperature leads to more configurations for filling those energy levels. And so as you go down the list, you're going more atoms per molecule, which again will give you more energy states and more possible configurations of filling those energy states. So typically, the more atoms per molecule, the higher the entropy.
In general, the more complex a molecule, the greater its entropy. We can see this trend by comparing 3 alkane molecules. The amount of motion for each molecule translates into entropy. The more motion overall, the greater the entropy.
And so again, I think the best way to think about it is more energy states accessible, the more possible number of configurations of those energy states, the higher the entropy. Entropy also depends on intermolecular forces. The stronger the intermolecular forces, the fewer the number of configurations, and the lower the entropy. And so which has higher entropy, MgO or magnesium oxide or sodium fluoride? Now they're both ionic solids. And so hopefully you remember from Chem 112 that the strength of intermolecular forces for ionic solids depends on charge first and then size. And so MgO, you have a +2 and -2, sodium fluoride a +1, -1. And so the MgO should have a stronger intermolecular force and a lower entropy. And so we see magnesium oxide's entropy is 27 versus sodium fluoride, which is 52.
The entropy of a solid depends on the strength of the forces holding it together. The weaker the attractive forces, the greater the motion of the ions in the crystal lattice, and the greater the entropy.
And so if you remember from 112, lattice enthalpy is a good measure of the ion-ion interaction, the strength of the ion-ion interaction. And so here we have entropy in the y-axis versus enthalpy on the x-axis. And so the larger the lattice enthalpy, the higher the ion-ion interaction, and the lower the entropy. The lower the lattice enthalpy, the higher the entropy. And so again, the stronger intermolecular force, the lower the entropy. The weaker intermolecular force, the more configurations, the higher the entropy. And again, for ionic solids, the most important consideration is the absolute charge. And so the larger the charge, the stronger electrostatic attraction, the larger the last enthalpy, the smaller the entropy, and the higher the melting point. Once you put in order of charge, you look at the size. The smaller the ions, the closer the ions, the stronger electrostatic attraction, the larger the last enthalpy, the smaller the entropy, and the higher the melting point. Entropy depends on phase. Typically, gases have higher entropy than liquids, which have higher entropy than solids. For a specific compound, the gas will always have the highest entropy, and the solid will always have the lowest entropy.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
And again, entropy is a measure of number of configurations. It is not a measure of disorder. And so for a compound, the gas always has the highest entropy and the solid will always have the lowest. So which should have a higher entropy, ice or liquid water, and so it should be liquid water. For a compound, again, the gas will always have the highest entropy, the solid will always have the lowest entropy. Now you can see sometimes where liquid will say have a lower entropy than a solid. Here in our list we have water, liquid water having entropy of 70 versus calcium carbonate, which has 93. But for a compound, the gas will always have the highest entropy and the solid will always have the lowest entropy. And it's kind of cool, we can actually plot the entropy as a function of temperature. And so if we're starting at 0 Kelvin, our entropy is starting at 0. Again, the third law says that the entropy of a perfect crystalline substance is 0 at 0 Kelvin. And then as we heat it, our entropy is going to increase. When we go through a phase transition, we'll see a jump in entropy. Once we get to the solid-liquid transition, again melting, going from the solid to liquid, you'll see a significant increase in entropy. As you're heating it, as you're adding higher temperature, entropy always increases with temperature. And then again, once you get between the liquid and the gas, you'll see a jump in the entropy. And so a gas will always have a higher entropy than the corresponding liquid, which will always have a higher entropy than the corresponding solid. And higher temperature always corresponds to higher entropy. So entropy changes dramatically at phase transitions. Enthalpy actually has a similar dependence. For gases, will have higher enthalpies than liquids, which has higher enthalpies than solids. Remember, as you go from a solid liquid gas, you have to add temperature, you add heat. If you're going from a gas to a solid, you're going to take heat away. Should the entropy of a compound increase or decrease with increasing temperature? And so increasing temperature always means more energy states are accessible, and so more possible configurations of those energy states, and hence the higher the entropy. Entropy always increases with increasing temperature. If you remember, we're talking about gases, and so here, y-axis, we have number of gas particles, x-axis, we have speed, and so T3 is higher temperature than T2, which is higher than temperature T1, and so the highest temperature, you notice they have the broadest distribution, largest number of configurations, and so higher temperature for gas always means higher entropy. And again, more states accessible, higher entropy.
Heptane at 1500 Kelvin has significantly greater molecular motion than it does at 200 Kelvin. The substance has greater entropy at 1500 Kelvin than at 200 Kelvin.
Entropy increases when a pure liquid or solid dissolves in a solvent. And so when you take ionic solid, you dissolve in water, you'll have more possible configurations, and so you'll have a higher entropy.
When potassium permanganate dissolves, its crystal lattice is broken apart, leading to an increase in disorder, and therefore an increase in entropy.
And so again, you think about it in terms of the number of configurations. Having to dissolve ionic solid has more possible configurations, more possible places those ions can be, and hence a higher entropy. So which substance in each pair has a higher entropy? And so here we have methane versus C3H8. Now notice they're both gases. Now typically for gas, intermolecular forces are negligible, so intermolecular forces shouldn't take into consideration. Phase, they're same phase, so phase doesn't matter. And so C3H8, more atoms per molecule, you'll lead to more energy states, and so more possible configurations. And so C3H8, which is propane, should have a higher entropy. Here we have potassium chloride aqueous versus potassium chloride solid. Now aqueous means dissolved in water, and so we saw that when you dissolve ionic solid in water, its entropy increases, and so potassium chloride aqueous should have a higher entropy. Now here we have helium gas versus krypton gas, again the same phase, and typically for gas, intermolecular forces are negligible, but you should remember that here you have noble gases, the only intermolecular force present is London dispersion, and the more massive, the stronger interaction. And so krypton's more massive, and so it's going to have a lower entropy than helium. Helium will have a higher entropy. Remember, weaker intermolecular forces leads to higher entropy. So H2O liquid versus H2S liquid, and so the same phase, same number of atoms per molecule. Now water, you have hydrogen bonding, so stronger intermolecular forces than H2S, and so H2S should have the higher entropy. Methane versus C2H6, again they're both gases, and so both of these are non-polar, and so they should have similar intermolecular forces. C2H6, more atoms per molecule, more number of energy states, more possible configurations, so C2H6 should have a higher entropy. Oxygen gas at 273 Kelvin or oxygen gas at 450 Kelvin, both are 1 atmosphere, and so again higher temperature should lead to a higher entropy. Put the following in order of increasing entropy, assuming that the same temperature, and so we have liquid gas, and so the gases will have the higher entropy than the liquids. And then within these pairs, remember phase is probably the most important consideration when you're looking at entropy. Now within these pairs, more atoms per molecule typically should give you the higher entropy. And so the highest entropy is probably the ethanol vapor, and then methanol, and then ethanol liquid, and then methanol. And so again, phase is typically the most important consideration. And then we're looking at the number of atoms per molecule. Now the intermolecular forces are pretty similar. They both have hydrogen bonding. Put the following in order of decreasing entropy. And so all these are ionic solids. And so again, the strong intermolecular force, the lower the entropy. The weaker intermolecular force, the higher the entropy. And again, for ionic solids, the charge is the most important consideration. And so we look at the charge of the ions. And so magnesium oxide, strontium oxide are both +2s and -2s. And so they should have the lowest entropy. The sodium chloride and the potassium bromide, +1, -1, so that should be the highest entropy. So we do it in terms of charge first. The larger the absolute charge, the stronger the attraction, the lower the entropy. And then to distinguish between ionic solids with the same set of charges, we look at the size. The smaller, the closer, the stronger. And so magnesium is higher in the periodic table than strontium, so it should be stronger interaction. And so the magnesium should have the strongest ion-ion interaction and the lowest entropy. And so again, for ionic solids, you look at the ion-ion interaction, which depends first on absolute charge and then size of the ions. And so the stronger the ion-ion interaction, the lower the entropy, the larger the last enthalpy, and the higher the melting point. Which has higher standard molar entropy, diamond or graphite. And so graphite's kind of interesting. You can actually get a little bit of sliding between these planes. And so the diamond's going to have a lower entropy, and the graphite will have a little bit higher entropy. And this you can think of in terms of intermolecular forces. For the diamond, these carbon-carbon bonds are covalent, and so that's going to have pretty strong. And so entropy depends on composition. More amps per molecule, the higher the entropy. Depends on intermolecular forces. The stronger intermolecular forces, the lower entropy because of fewer configurations. Depends on physical state. For a specific compound, the gas will always have the higher entropy and the solid always have the lowest. In terms of temperature, higher temperature always corresponds to higher entropy. Now we can think about the universe as composed of two parts, the system and the surroundings. The system could be a beaker, the surroundings could be everything else. And we're going to define the system as a closed system, meaning that the only thing that transfers between system and surroundings is heat and work. Now the change in entropy of the system, we can think about change in entropy of the reaction. Now, if we want to calculate change entropy for a system and for a reaction, we can do products minus reactants. And so if you remember when we talked about enthalpy previously, we can calculate the change in enthalpy for a reaction by doing products minus reactants. We can also do that for entropy, products minus reactants. And so this sign here corresponds to the sum. So you add all the entropies of the products minus all the entropies of the reactants. And so if the products have higher entropy than the reactants, then the change in entropy for the reaction will be positive. Again, that corresponds to the change in entropy for the system. If we look at an example, here we have methane plus oxygen goes to CO2 plus water vapor. And so we have products, the carbon dioxide plus the water vapor minus reactants, the methane plus the O2. Now notice that the coefficients come down here, so you multiply the entropy times 2 because you have that coefficient 2 there. And so we look up the table, we can find those values, and we see that the change in enthalpy for this reaction is minus 4. And again, delta S for the reaction corresponds to delta S for the system. Remember, you have the universe is equal to the system plus surroundings. That corresponds to universe. Here, we're looking at delta S for the system. When the following reaction occurs, does the entropy of the system increase or decrease? Now, often for a reaction, if you just look at the number of gas particles, you can determine the delta S of the system. And so we're going from 2 gas particles to 3 gas particles. And so most likely during this reaction, delta S of the system should be positive. If we look at this reaction, we're going from 3 gas particles to 2 gas particles, and so delta of the system should actually be negative. And so if you flip a reaction, so if we take this reaction and write the products as reactants, reactants as products, that changes the sign of delta S for the reaction. When salt is dissolved in water, does the entropy of the system increase or decrease? So if you go from sodium chloride solid to sodium chloride aqueous, remember we saw that the aqueous has higher entropy, and so delta S of the system is products minus reactants, and so our products have higher, and so delta S of the system should be positive. And again, you can think about it in terms of number of configurations. The aqueous solution has more configurations in terms of positions than the solid. And so, again, please remember, entropy is not about disorder. It's about the number of configurations. Thanks to poor Dr. Boltzmann, we know that entropy is equal to K natural log W, where K is Boltzmann's constant. ln W is the natural log of the number of configurations. Now, configurations could be in terms of positions, orientations, or ways of filling energy levels. And then we can relate these to composition. More atoms per molecule, more energy states, higher entropy. Weaker intermolecular forces, higher entropy. Gases have higher entropy than liquids, which have higher entropy than solids. Higher temperature always corresponds to higher entropy. I hope that helps.